The voltage-current relationships for capacitors and inductors contain derivatives. That means that the equations for circuits that contain capacitors and inductors will be differential equations. In this video, I'll talk about differential equations governing circuits with one energy storage element. First, I'll quickly review some fundamentals relative to electrical circuits that contain energy storage elements. Systems that store energy are commonly called dynamic systems. For these types of systems, we have to treat the inputs and the outputs as functions of time. Since the system can store energy, the system in some sense remembers the past, which means that the energy stored in the system depends on the system energy at previous times. Since the governing equations for energy storage elements contain derivatives, equations governing the systems with energy storage elements are differential equations. Differential equations govern the rate at which energy can be stored or released by the system. We've already talked briefly about one example of a system that stores energy, a mass sliding on a surface that has some friction. This system stores energy in the velocity of the mass. The kinetic energy of the mass is the mass times the square of the velocity. The system also dissipates energy as heat because of the sliding friction. Suppose we apply this force to the mass. The force is a constant that pushes the mass to the right. The force is suddenly removed at this time. This is a plot that shows the corresponding velocity of the mass. If a constant force is applied for a long time, the mass's velocity will become a constant, since the energy added to the mass by the force is exactly balanced by the energy dissipated as heat. When the force is removed, we're no longer adding energy to the system, but energy is still being dissipated by the friction. This means the mass starts to slow down. The velocity after removing the force decays exponentially, beginning at the initial velocity v0. The rate of decay of the exponential is governed by the time constant, tau, which depends on the mass and the friction between the mass and the surface. For example, a high friction will cause the mass to slow down more quickly. A similar example is the process of heating a frying pan. Heat is the input to the pan, provided by a stove burner. The temperature of the pan will be our output. Heat energy is stored in the frying pan as temperature. The higher the temperature, the more heat is stored in the pan. Suppose we suddenly start adding heat to the pan as shown here. The heat input from the burner is 0 for time less than 0, and then it suddenly changes to a positive constant for time greater than 0. The temperature increase resulting from this heat input looks like this. The pan temperature increases from its original room temperature value. As the temperature increases, the heat dissipated by the frying pan to the atmosphere increases. As the heat dissipation rate increases, the rate of temperature change slows. Finally, as the heat input from the burner is matched by the heat dissipation to the atmosphere, the temperature again becomes constant. The shape of this curve is again modeled with an exponential. Both of the previous examples are what are called first-order systems. That means that they have one energy storage element. In the sliding mass example, the only way to store energy is as the velocity of the mass. In the frying pan example, the energy stored is indicated by temperature. By definition, first-order systems are governed by first-order differential equations. The order of the differential equation governing a system is equivalent to the number of independent energy storage elements in the system. This is what I'll call the standard form of a first-order differential equation. In this form, the multiplicative factor on the highest order derivative, dy by dt, is equal to 1. If this term is 1, then the multiplicative factor on the 0th order derivative is 1 over the time constant. By writing the differential equation in this form, we can immediately see the time constant of the circuit. We've already seen that the responses of first-order systems contain an exponential with some time constant, tau. The differential equation written in this form directly tells us what the time constant is, which in turn tells us how quickly the system responds. Now that we've gotten a general idea of the form of the governing equations and responses of first-order systems, let's do some more detailed analysis of first-order electrical systems. Our first example will be what is called an RC circuit, which stands for resistor capacitor. This type of circuit contains one capacitor, so it has one energy storage element, and its input-output equation will be a first-order differential equation. The remaining elements in the circuit are sources and resistors. I'll determine the response of this circuit consisting of a capacitor connected to a resistor that's in series with a voltage source. The input is Vs of t, and the output is the voltage across the capacitor, Vc of t. Notice that this circuit that's connected to the capacitor consists of a Thevenin equivalent circuit. Since any linear circuit can be modeled as a Thevenin circuit, this circuit is an appropriate model for any circuit containing one capacitor. To derive the differential equation, I'll first label the current through the capacitor. The current has to enter the positive voltage terminal, and the current is C, the capacitance, times dVc by dt. If I do KVL around this loop, starting down here, I see the negative terminal on Vs first, so minus Vs, plus the voltage across this resistor. KCL here says that the current through this resistor is C dVc by dt. So this voltage is the resistance, RTh, times the current, plus RTh times C dVc by dt, plus the voltage across the capacitor, which is just Vc of t. That sums to 0 since it brings us back to our starting point. Now I'll divide out this RTh times C term to get a 1 in front of the highest order derivative and move V sub s to the other side. So dVc by dt plus 1 over RTh times C times Vc is equal to 1 over RTh times C times Vs. With a 1 in this position, this term here is equal to 1 over tau. So tau is equal to RTh, the Thevenin resistance, times the capacitance. My second example will be what's called an RL circuit, which stands for resistor inductor. The circuit contains only one energy storage element, an inductor, so its input-output equation will be a first-order differential equation, and this is also a first-order circuit. In this example, I'll look at a circuit consisting of an inductor in parallel with a resistance and a current source. Notice that this section of the circuit corresponds to a Norton equivalent circuit connected to an inductor. Since any linear circuit can be modeled as a Norton equivalent circuit, this circuit is an appropriate model for any circuit containing one inductor. To derive the differential equation, I'll first label the voltage across the inductor. The inductor voltage is the inductance times the derivative of the current. Notice that I've defined this such that the assumed positive current direction is entering the positive voltage terminal. Now let's do KCL at this terminal. In order to do KCL, I need the current through this resistor, which I'll call IR. IR is this voltage divided by the Thevenin resistance. Now KCL, Is of t is entering the terminal, so I'm going to call that a negative contribution, plus IR, which is L over RTh times DIL by dt, plus the inductor current, which is IL of t. That sums to 0. Now divide out this term, multiplying the highest order derivative, DIL by dt plus RTh over L times IL is equal to Is times L RTh over L. With this term being a 1, this term is 1 over tau, so the time constant for an RL circuit is equal to L over RTh. Now let's briefly review the formulas for time constants of first-order circuits. An RC circuit has one independent capacitor connected to a network of resistors and sources. Independent capacitors can't be combined into a single equivalent capacitance. For example, two capacitors in either series or parallel can be combined into a single equivalent capacitance, so they would count as only a single independent element. For this type of circuit, the time constant is equal to the product of the capacitance and the Thevenin equivalent resistance seen by the capacitor. The other option for a first-order electrical circuit contains one independent inductor as its energy storage element. Multiple inductors in series or parallel can be combined to a single equivalent inductor in the same way as capacitors. The independent inductor can be connected to a network of resistors and sources. For this type of circuit, the time constant is equal to the inductance divided by the Thevenin equivalent resistance seen by the inductor. Now let's do an example of determining the differential equation for an RL circuit and use that equation to determine the time constant of the circuit. When finding a differential equation, I'll always label the voltages across the inductors. So 4 times the derivative of the current IL with respect to time. Notice that assumed positive current enters this assumed positive voltage terminal. Now let's do KCL at this terminal. I have IS entering. I'll treat that as a negative term. So negative IS plus the current through this leg, which is just IL since these two elements are in series, plus the current through this leg, which is this voltage, V4 divided by 4 ohms. So this is going to be 1 over 4 ohms times whatever this voltage is. I can find this voltage by doing KVL around this loop. These two elements are in series, so the voltage across the resistor is 2 ohms times IL, and this is 2 times IL. Starting down here, I get a negative 4 DIL by dt minus 2IL. My loop is entering the negative terminals on both of these, plus V4 is equal to 0. So V4, this voltage, is equal to 4 DIL by dt plus 2IL. Now the current that I want over here is 1 over 4 ohms times 4 DIL by dt plus 2IL. That sums to 0. Doing the math, I get IS is equal to IL plus 4 divided by 4 is 1, DIL by dt, plus 2 over 4 is 1/2, IL is equal to 0. So this equation becomes DIL by dt plus 3/2, 3 over 2 IL, is equal to I sub s. Since I have a 1 multiplying the highest order derivative, this term is 1 over tau, so tau is equal to 2/3 of a second. We can check the time constant we got on the previous slide by determining the equivalent resistance seen by the inductor and then plugging that into our formula for the time constant of an RL circuit. I can get the Thevenin resistance seen by the inductor by killing the sources, so my current source becomes an open circuit, so there's no current through here, and determining the voltage-current relationships across the inductor terminals. So what I'm doing is applying a little hypothetical voltage and determining the resulting current. Since this current is 0, all of the current going through the 2 ohm resistor will also go through the 4 ohm resistor, and those two resistors are in series. So RTH is the sum of 2 ohms and 4 ohms, which is 6 ohms. For an inductor, tau is equal to L over RTH. The inductance was 4 henries over 6 ohms, so tau is equal to 2/3 of a second, which is the same result we got previously. Now I'll do an example of determining the differential equation for an RC circuit and determine the circuit time constant from that differential equation. First, I'll label the capacitor voltage, which is already done. The capacitor current is the capacitance, 1/2 of a farad times the derivative of voltage. Now I'll do KVL around this loop, but I need the voltages across the 3 ohm and the 1 ohm resistor. They both share the same current. The current out of the source goes through this one, it gets split up and goes through these two, and then comes down through here. So from KCL at here, IS is equal to this current through the capacitor, which is 1/2 dVc by dt plus the current through the resistor. Since these two are in parallel, a loop around there says that they share the same voltage difference. So this voltage is also Vc of t, and this current is Vc over 2. Now let's do my KVL around this loop. So I have minus Vs plus 3 ohms times Is. Is is 1/2 dVc dt plus Vc over 2. Plus the voltage across the capacitor, which is just Vc, plus this voltage, which is 1 ohm, times Is, which is still 1/2 dVc by dt plus Vc over 2, and that sums up to 0. Combining terms here, I get Vs is equal to 3/2 plus 1/2 is 2 dVc by dt plus 3/2 plus 1/2, which is 2, plus 1 Vc, which is 3 times Vc. Dividing out this term gives me dVc by dt plus 3 over 2 Vc is equal to 1/2 Vs. With the 1 multiplying the derivative term, this is 1 over tau, so for this circuit, tau is equal to 2/3 of a second. Alternately, we can determine the Thevenin resistance seen by the capacitor and use that to determine the time constant. If I kill the independent sources, the voltage source becomes a short circuit. The Thevenin resistance is a voltage-current relationship across these terminals. The 3 ohm and the 1 ohm resistor are in series. Any current that goes through here will also go through the 1 ohm resistor. Combining those in series gives me this circuit. The 2 ohm resistor doesn't matter yet. Combining these two in series gives me 4 ohms. Now if I loop around here, these two share the same voltage difference, so they're in parallel. Combining them in parallel, RTH is equal to 2 ohms times 4 ohms over 2 ohms plus 4 ohms, which is 8 over 6 ohms. The time constant for an RC circuit is the Thevenin resistance times the capacitance, which is 8 over 6 ohms times the capacitance was 1/2 of a farad. So tau is 4 over 6 seconds, which is 2/3 of a second, which is the same result I got from the differential equation. I won't get into the details of solving differential equations until the next video, but there are a couple of things I want to mention before we solve the governing equations. First, in order to solve a differential equation, we need an initial condition. This is just the value of the response variable at some initial time. In our problems, we'll typically be looking for responses for time greater than 0. So we need a value of the response variable just after time t equals 0, denoted here as time equals 0 plus. The plus denotes a time infinitesimally soon after 0. In order to determine the initial condition, we'll use the property from Unit 7 that energy can't change instantly as long as finite power is applied to the system. For electrical circuits, this means that capacitor voltages and inductor currents can't change instantly. As an example, let's take a look at this circuit. We have a 3 amp source here, and we close this switch at time t equals 0. If we want the response of the inductor current for time greater than 0, we need an initial inductor current just after the switch closes. We need the inductor current at time t equals 0 plus. We can do this by finding the inductor current before the switch closes. Since inductor currents can't change instantly, this is also the inductor current just after the switch closes. This then is the circuit we want to analyze. Just before the switch closes, the switch is an open circuit. The input's constant, and this switch has been in this position for a long time, so all the voltages and currents in the circuit have become constant. That means that the inductor looks like a short circuit. Since this is a short circuit and this current is 0 amps, all of this 3 amp source current is going through this inductor, and I sub L at t equals 0 minus is equal to 3 amps. Since inductor currents can't change instantly, that means that the inductor current at t equals 0 plus, just after the switch closes, is also 3 amps. And that's our initial condition. Finally, before we go to the effort of solving our differential equations, we can quickly double check the equations to make sure they make sense. If the original equation is obviously wrong, there's no reason to expend the energy necessary to solve it. The way we'll do this is to check the response to a constant input. This doesn't mean that the actual input signal we're going to analyze is constant. This is just a simple test case. If the input is constant, all of the voltages and currents in the circuit eventually will become constants. That means that inductors can be modeled as short circuits and capacitors as open circuits. The response of the resulting resistive network can be compared to the response of the differential equation to a constant input. If the two approaches agree, the differential equation is likely correct. As an example, let's look at this circuit. We determined a differential equation for this circuit previously, but now let's modify the circuit slightly. We'll change the input to a constant value I sub s instead of a time-varying function. We'll also wait for a long time to make sure that the current through the inductor has become constant. Under these conditions, the inductor looks like a short circuit. And the current I sub L as t goes to infinity can be determined from a current divider. So that's the total current I sub s times the other resistance, which is 4 ohms, over the sum of these two resistances, 2 ohms plus 4 ohms. So IL of infinity is 2/3 of I sub s. Now let's compare this response to the response we'd expect from the differential equation. This is the differential equation we previously found for this circuit with a time-varying input. If this input term is constant, say I sub s, then if the right-hand side is a constant, the left-hand side has to be a constant. And this derivative term has to be 0. That means that as t goes to infinity, 3/2 I sub L of infinity is equal to I sub s, and I sub L of infinity is equal to 2/3 I sub s. The two approaches match, so that means that this original differential equation is probably correct. In this video, I've talked in very general terms about how the responses of first-order circuits contain exponential functions. In the next video, I'll talk in more detail about the responses of first-order systems and the solution of the differential equations governing those systems.